This is section 4.6, rational functions and models. These are the topics we will cover in this section. A rational function can be represented by f of x equals p of x over q of x, where p and q are simply polynomials, and we insist that q of x does not equal 0 because we cannot divide by 0. Now the reason we study rational functions is to kind of introduce ourselves to the concept of asymptotes. We have two types of asymptotes we're going to focus on, with the third we'll introduce at the end. The first is what's called a vertical asymptote. Vertical asymptote is simply a dotted line or imaginary line x equals k, of which a function never crosses that line. What happens is as we get close to that line, the function either shoots up to infinity or it shoots down to negative infinity as we get closer and closer to that line. Now we could have them both shoot up to infinity or both shoot down to negative infinity, or we could have them go opposite directions. A vertical asymptote exists for all values of the domain, all values of x, because it won't be part of the domain, all values of x which actually cause the denominator to be equal to 0, but it also has to not make the numerator equal to 0. There's what's called a horizontal asymptote as well. A horizontal asymptote is a horizontal line which your function approaches. It can actually cross this line, unlike a vertical asymptote, but typically what happens as your function goes far to the left or far to the right, it will approach an imaginary horizontal line. So as x goes to negative infinity to the left, or x goes to positive infinity to the right, the function approaches this imaginary line y equals b. Now we can actually take rational functions and do some of what we've already done with things before. We've shifted functions around. We looked at the graph of f of x equals 1 over x squared. That's this graph. We haven't really studied it much yet, but I can get the graph of g of x equals 1 over x minus 2 squared plus 3. We know the negative 2 is inside the function, so it shifts left and right, and it does the opposite. So this negative 2 here actually translates the graph 2 units to the right. So this vertical asymptote at x equals 0 shifts 2 units to the right and now becomes a vertical asymptote at x equals 2. This plus 3 is outside the function, so it shifts the function up by 3 units. So this original asymptote of y equals 0, which is the horizontal asymptote, is now shifted up 3 units to y equals 3. So here's my new asymptote. So I now have new asymptotes of x equals 2 and y equals 3, but the original graph remains the same. All I've done is translate this graph to the right 2 and up 3. Now that we kind of see how they work, how do we actually find vertical asymptotes? Well, to find vertical asymptotes is very simple. All we do is set our denominator, this q of x, equal to 0. Now, whatever number, say k, makes this denominator 0, then x minus k is an asymptote. However, we do have to watch out for one thing. We need to plug k back into p, because if k makes q 0 and it makes p 0, it's not an asymptote. It's actually what's called a removable discontinuity, and we have to treat it differently. Let's look at these couple examples. We have f of x equals 5 over x squared minus 9. To find the vertical asymptote here, all I do is set my denominator equal to 0. So x squared minus 9 equals 0. So that means x is plus or minus 3. Well, my numerator is constant, so it'll never be 0. So therefore I have vertical asymptotes at x equals 3 and x equals negative 3. If I look at this next one, g of x equals x minus 2 over x squared plus 3x minus 10, I'm going to take my denominator and I'm going to set my denominator equal to 0. And this simply factors to x plus 5 times x minus 2 is equal to 0. And if x plus 5 times x minus 2 equals 0, that means either x equals 5, negative 5, or x equals 2. Now again, we have to check these, because if we take 2 and plug it into the numerator, it makes the numerator 0 also. So x equals 2 is not a vertical asymptote. Only x equals negative 5 is a vertical asymptote. In fact, I can actually factor out an x minus 2 from the numerator and the denominator and rewrite g of x as 1 over x plus 5. And that's a better example of the graph that it actually is. It has what's called a removable discontinuity at x equals 2. In other words, there's just a hole in the graph at x equals 2. Let's look at finding the horizontal asymptotes. Finding horizontal asymptotes is a little bit different. If you remember our discussion of polynomials, we keep talking about the degree of a polynomial. And this is what we're going to use to find horizontal asymptotes, are the degrees. We want to find the degree of the numerator, the p, and the degree of the denominator, the q. If the degree of the numerator, if the degree of p, is less than the degree of the denominator, the degree of q, then I have a horizontal asymptote at y equals 0. If the degree of the numerator is greater than the degree of the denominator, there's simply no horizontal asymptote. And if the two degrees are equal, then the horizontal asymptote occurs at y equals, it's actually a ratio of the leading coefficient of the p over the leading coefficient of the q. Let's see how this happens. Our first example will go back to our one we did earlier, f of x equals 5 over x squared minus 9. In this case, the degree of p is 0, the degree of q is 2, so the degree of p is less than the degree of q, so I have a horizontal asymptote at y equals 0. In my next example, I have g of x is 3x squared. Sorry about that. G of x is 3x squared minus 2 all over 4x squared plus 3x minus 10. Notice the degree of the numerator is 2 and the degree of the denominator is 2. Since they're both equal, I got to look at their leading coefficients. The leading coefficient of the numerator is 3. Leading coefficient of the denominator is 4. Therefore, I have a horizontal asymptote at y equals 3/4. The last type of asymptote we're going to talk about is what's called an oblique asymptote. And this is simply a straight line. It's not a horizontal vertical line. It's a slanted line, okay, but it's still straight. And this occurs when the degree of the numerator is simply 1 more than the degree of the denominator. And to get this equation for this line, we simply have to divide the numerator by the denominator. We have to do synthetic division. And the quotient that we wind up with, not the remainder, just the quotient part, becomes the oblique asymptote.